Short video on how to do these namings. In my class freshman year this year, you're going to be allowed to use a naming set. So all you need to do is be able to follow your own rules. So understanding them is key. So I got a periodic table over here. And the key thing is, again, this line that goes right here. Bonk, 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 bonk. Everything on this side of it is those metals. Those are the ones that have the weak grip on the attractions for valence electrons. And the ones over here are the strong, the non-metals. And you have to be able to identify those guys. Simple thing. So when we look over here in magic, they're right about here, you are going to see a chart appear with a clear little guide. There's three types of bonds we're looking at: metallic, covalent, and ionic. And at the end of the day, they're all the same. The logic between what makes one and one makes another is just the difference in how strong they grab those electrons. So we have metallic, because when they're both from this side of the periodic table, that's rule set A. But we can't name those. So there's going to be an X. Covalent is when they're both from non-metal. That's over here. That's where we're going to have rule set B. Right there is when they are covalent. And finally, C is when they are ionic, and that's one from both sides. Now, there's a caveat there. A little hitch is that if the metal comes from this little part, then it's going to have a different set of rules than if the metal comes from over here or over here. These are called transition metals. And the thing is, the periodic table is really good at telling us charges, +1, +2, +3. But these guys, it does not. So we're going to have to do something else in order to know what those guys' charge is when we name them. So this video may be one and maybe three different parts. You'll see as I post it as we go through. So first is naming covalence. So if your first step says they're both from over here, non-metals, then how do we name them? So we're going to follow that here. So if covalent. So if they both are coming from that side of the periodic table. Both that side. So what do? Two sets of rules that you should have on your card: name to formula, formula to name. In order to name these guys, though, you do have to know the Greek prefixes. The earlier ones will show up more often, but I'll have them all magically appear. There they are. If you're going to need to write them down in your note card, that's okay. That's up to you. As you use them, they'll sink into your brain and you won't have to look anymore. So mono, di, tri, that just means 1, 2, 3, 4. So the example I'm going to use for this guy is an old friend. We are going to use carbon dioxide. You're all familiar with it, so it should be easy, and it shows a couple things I want to do with these rules. So rule number 1, those symbols, we got to make those, names, we want to make symbols. So carbon, right here on your periodic table, it's a C. And oxide, that's oxygen, right here. So again, definitely covalent, because they're both from that side of the periodic table. Step 2, if it has prefixes, like di, those prefixes become subscripts. So there's nothing before carbon, so that means just 1. The di means 2, so this is CO2. And you're done. 2 quick steps. If you're going the other way, let's say we wanted to go back from CO2, formula to name. Step 1, exact opposite. It said names to symbols. We want symbols to names. So C is carbon. O is oxygen. C is carbon, O is oxygen. 2, exact opposite. Instead of the prefixes becoming subscripts, we're going to have our subscripts become prefixes. It's just the opposite. So there was nothing in front of carbon, so that just means 1. And 2 here, dioxygen. So we have not carbon, this is going to be dioxygen. But I'm going to skip this next step because 3, there's 2 little caveats. Change the ending to I, that's like the period at the end of your sentence, so you know you're there. And there's a wee little rule here saying don't start with mono. If mono shows up anywhere else in the second spot, you use it, just don't start with mono. So it's not going to be monocarbon dioxide. Don't start with mono, just carbon dioxide. And that's how you do covalence. And we're here at the 5-minute mark, moving on. How to do ionics. So if it's ionic, and we're going to start with the easier one, without a transition metal. Okay, so if it's ionic without a transition metal, so up here, that would have been C2 is on our original flow chart. C2 up there. All right, so name to formula. Formula to name. Just like above. So these are examples. One's coming from both sides of the periodic table, but again, our metal is not coming from that middle part. It's coming from the part that we clearly know that first one is a +1 charge when we do our shielding effect and Bohr modelings. We know the second one is a +2. We got those transitions again where we don't know what's going on. And then +3 all the way down to, well, the next one, carbon, it can be plus or -4. That's the in-between. When you get to this next family, so here it goes to -3 at the nitrogen, -2, -1. Noble gases are 0. They do not ionize easily. So you need to know that. Why do you need to know that? You'll see in a second. So name to formula. We're going to do formula to name first, though, because it's easier. So let's say I have CaCl2. This is something you easily know. You put it on your sidewalks in the wintertime as a salt. Same as before. Symbol to name. So Ca is calcium. Cl is chlorine. Step 1. Again, after you've identified that this is ionic. Step 2. End it with "-ide". And you go, what about those prefixes, the mono, the di, the tri? Don't show up here. Those are only covalents. If you ever have a metal with a prefix, you made a mistake. So it's just calcium chloride. How do I know to cut it off at chloride instead of chlorinide? At first, I don't care. As you gain experience with it, it'll just sound right to cut it off in the right place. So don't worry about memorizing all these different places that you could do it. Just cut it off where it sounds good, as long as you follow the rules. So how do we go the other way? Name to formula. If we start off with calcium chloride, how do we know how to do it? All right, step 1, should be familiar by now. Name to symbol. So Ca, Cl. Number 2, how do we know what these guys are going to be? So you have to find their charges from the periodic table. And I just showed you how to do that a few seconds ago. So calcium is +2, chlorine is -1. Again, calcium is +2 because it is here in this +2 column, and chlorine is here, so it is a -1. Looks like one column is off my screen here, so I apologize for that. So +2, -1. And there's lots of ways to do it. So if you want a different way of doing it, let me know. The one students usually prefer is crisscross reduce. And when I mean that, I mean you take the charge from one and you bring it down. You crisscross. Drop your positives or negatives. So the 1 goes here, and we don't write 1s as subscripts. And the 2 will go there. Does it reduce? 1 to 2 is already reduced, so you're good. Let me give an example of one that would reduce. Is like if you had calcium oxide, you would have ended up with a +2 and a -2. You would have crisscrossed, and it would have been Ca2O2, but that reduces to CaO. It's the same ratio. Put in the lowest term ratio. Crisscross, reduce. All right, last one. How to actually do this. If it's ionic with a transition. So the metal is coming from a part of the periodic table that we do not know its charge by looking at the periodic table. So there's going to be a small twist you're going to have to do in the naming in order to actually tell the reader what the charge is. So if as a transition metal, name to formula, formula to name, as we go through. So first step is here, name to formula. So we're going to go iron 3 oxide. You have to know your Roman numerals here. So step 1, Should be old by now. Name is going to become a symbol. So iron is Fe, oxygen is O. Just like before. Next step, find their charges. Thing is though, this one can be found from the periodic table. This one cannot. The periodic table will not tell you iron's charge, but that's what the Roman numeral is. This is the metal charge. So it actually saves you time. It looks like it's more confusing because you go, what's the Roman numeral? Saves you from having to look at the periodic table. So that's +3. And just like before, crisscross, reduce. So this fancy thing that sounded like iron 3 oxide is just Fe2O3. That doesn't reduce, so it's set. On this part, how do we go backwards? This one has different ways depending on which one your brain works on. So the last step on this one, if the way I'm going to show you here doesn't work, ask me. I've got like 3 different ways to do this at least. So let's say we're going from Fe2O3 and we want to know its name. Step 1 has all of them. Symbol to name. Iron, something in Roman numerals, oxide. And I know I'm going to need Roman numerals here because this is ionic, metal, non-metal, and iron is coming from the center part of the periodic table. So this pink block on this table is the transition metals, and they're going to need a Roman numeral. So how do you do it? Step 2, you're going to have to find their charges, just like you did before, but again, because the metal's charge needs to go here in the Roman numerals. So you're looking at this and you're going, okay, I can find oxygen's charge from the periodic table, but how do I find iron's? This is because you know that every electron that oxygen, the non-metal, got is because the iron lost. So if you can figure out how much negativity is over here, you can figure out how much positivity has to be over here because they have to balance. For every 1 electron these guys took, these guys had to lose it. So I'm going to do a little graphic version of this to try to model what's happening here in the math. So I have 3 oxygens, boom, 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 2 irons, boom, boom. And this -2 means each of these oxygens is going to take 2 electrons. I'm going to show that with little arrows there. These are the 6 electrons that these 3 took. So he's -2, he's -2, he's -2. Each had to take 2 electrons. Math ways, I can just do that by multiplication. 3 times 2 electrons each equal 6 electrons were stolen. So it becomes a little story problem. 3 oxygen atoms each took 2 electrons for a total of 6 electrons were taken. Multiply on the way up. 3 times 2 is 6. Ignore the negative sign. Then who do they steal the electrons from? The iron. So over here, you can just connect arrows in an even way. 2 to this guy, 2 to that guy, 1 to that guy, 1 to that guy. And you'll see that each of these irons lost 3 electrons. You lose 3 negative things, you're going to become +3 charge. So I already have the answer visually. If that works for you, fantastic, do that. But over here, a way to do that in math, 6 electrons were stolen from 2 irons. Divide on the way down, which means each iron lost 3 electrons. So this is going to be iron 3 oxide, because that's the charge of this guy. And that's how you do it. That's how you name every compound. If you're stressing out about this last step, a lot of kids see the math. Heads up, this is going to be like 1 or 2 points on the test. That's it. This is a skill that I want you to be able to use. It's nothing that you have to memorize yet. With practice and repetition, you will just learn it. It'll just happen organically. So in the meantime, I will copy what I just wrote and put that in the classroom. I'll put this video in the classroom with timestamps of where each type of bond was.